Hello everyone, welcome to our session, The Ride with WebAssembly. I'm Nipun and I've been working with Adobe for past few years and I've worked on multiple platforms and that's where WebAssembly comes into picture. I'd like my co-presenter, Pranay, to introduce himself.
Hello everyone, I am Pranay. I have been with Adobe for past several years and we have worked over multiple platforms. At the core, we are C++ developers and we have worked on web as well. So their WebAssembly has been a core part of what we have done past few years. And we would like to take you along on this ride and it's going to go a lot of places. So let's start with this. Thank you, Nipun.
Great. So I think let's target and let's strike down the elephant in the room, like why this talk. There have been like multiple talks in the past. Uh, I mean, one of the keynotes that I attended while I was in person, 2019, Ben talked about WebAssembly, but it was more around WASI. There were certain other precursor talks which are very good, but they revolved a lot around like ASM.js. And because like WebAssembly in itself is so evolving, there have been like so many recent developments that have been happening in that space itself. Like debugging is now super smooth with Dwarf. There is exception handling, which is there. Fixed with SIMD is there. Shared array buffer support has now been added to certain browsers, and also the other browsers. Basically, all the browsers are coming along with different specs that have been floated for WebAssembly. And for all those to actually look into what WebAssembly is. WebAssembly is basically a binary instruction format, which is run on stacked virtual machine. And it's basically made for portability, where you're trying to run your, let's say, C++ code or Rust code to actually on web. And it's the web would now run this binary format, which will be super fast. It's way like faster than the normal JavaScript execution that happens on the web as of now. So yeah, I mean, our intent of the talk is more around getting back to the basics, but also once somebody is given a task to actually port their own application to web or WASM, like what are the steps they have to take? What are the things that they have to keep in mind? And we want to like take this chance to actually introduce you to the core concepts of threading, file system, interfacing with C++, JS, and how can one go about it? And one shouldn't feel really daunted about it. So, I mean, that's where majorly our talk will try to fill in the place for. So, our agenda for the talk is basically divided into 4 blocks. The first is like basic WebAssembly and introduction to that. Then we'll get into like tooling and setup. And then we'll look into like what does it take to port a C++ project. And we'll interweave that with like a hands-on session of like looking at code and compiling and running it through. And then finally ending it with some debugging of WebAssembly and tips and tricks and cautions. All the examples that we quote in the session would be up and running and be available on the GitHub. It's basically the Docker file and the README file, everything is there. So shouldn't take long to actually set up apart from the initial Docker setup. I think the best way to follow this session would be look at this session. And then once you have done with that, like go ahead, clone this repo and then follow all the steps to do it by yourself on your own computer. So with that, I'll hand it over to Pranay to actually give us a good foundation for WebAssembly.
Thank you so much, Nipun. Let's see what WebAssembly really is. It's abbreviated as WASM. It's a portable binary format which is accepted across all the major browsers. The best thing about WebAssembly is you don't have to actually code in it. You don't program in it. It's a compilation target for you. So you at the core, you are still a C++ or Rust developer, but you enable the deployment on the web for client and server applications using it. So if you want to ship your library or your code across the entire web stack, this is the right ticket for you. It was created to support JavaScript, not as a replacement for it. And let's see what makes it fast compared to JavaScript. On an average, WebAssembly is approximately 4.2 times faster than JavaScript. Why it's fast? Because it's compact, it's a binary code itself. There is no parsing required, and it's very close to a machine code. Now, for a typical interpreted language, there are 2 steps. That is, it needs to be compiled, and then it runs inside the browser. For WebAssembly, it's already compiled, so there is no two-stage compilation required, and there is no garbage collection that happens. The key advantages that WebAssembly provides us is that it's efficient and fast because it's a WASM stack machine, which is encoded in a size and load time efficient format. So the speed is not as good as native, but pretty close, and hopefully it would get better as we move on. Then it's open and debuggable. It's pretty printed in a text-like format for better debugging and testing. And there are some browsers that provide source code level debugging as well. WebAssembly modules are easy to plug. They can be ported. They can call into and out of the JavaScript context very easily. We'll cover that in the presentation. And the last part is it enforces the same origin permission policies that a browser enforces. So your WebAssembly code is still safe from the browser policies that are being enforced. It's memory safe, and the execution is done in a sandbox environment. What would you need in this ride? Just like a typical native dev environment, WebAssembly also lies on two main pillars. First is an execution target, that is the browser or your Node.js environment. Since Chrome supports most of the WebAssembly features, it's the most widely accepted browser. We have used Chrome as an execution target here. Then second is the compilation toolchain, just like GCC and Clang on the native environment. So emscripten is the most popular and actively developed toolchain for WebAssembly. It can be assumed as a thin wrapper over LLVM, and it is the most actively developed. There are consistent developments happening in emscripten. So we have used that as the default toolchain here. And whatever features would work well on the runtime, that actually depends on these two pillars, that is execution target and the compilation toolchain. You can check the support easily by can I use.com/wasm, which browser support which features, and emscripten has a fantastic documentation at its own portal. Now, WebAssembly don't like to brag about it, but there have been some notable projects ported to web via emscripten. That is SQLite. It's available through SQL.js. Then the font rendering engine FreeType is also there. FFmpeg, the most famous one, your audio video encoder decoder is there. Games like Unreal Engine 4 and various engines such as Unity and Doom 3, these are also available. VI Improved also is ported to web via emscripten. WebAssembly is designed with the web's openness in mind. So there's a text format dumped by the compiler as an IR stage along with the WASM code. So when you try to debug any WASM in browser, it shows that WAT format by default for better readability. There also exists a superset that is known as WEST. It's not officially in the spec, but it's used sometimes for testing purposes. With that, Nipun will take you on the ride for tooling and setup part. Handing over to you, Nipun.
Thanks, Pranay, for setting our foundation really well. I think as Pranay mentioned, the choice of the compiler that we're going to use for compiling our C++ code to WASM would be emscripten. Now it's pretty simple to actually set it up on your own system. You clone the repository, you install the latest SDK, and then you activate that on your shell, and you can use the appropriate shell script that based on the platform that you're on. And emscripten is basically a thin wrapper over LLVM. So it should be pretty familiar for anybody using Clang. Much of the similar options are available there. There are options available for debugging, optimization. You can control the output if you want like a JS or a WASM or an HTML output as well. One of the things which is different among the two, which is like GCC and Clang and EMCC, is that while in GCC and Clang, you might just have to like give the new like the linked libraries or the link like the header include folders. But for EMCC, for enabling and disabling enabling features, you also like have to give certain feature flags to it. So let's say you want to set the total memory that your WASM can take. You can use the total memory flag with it. Now the default is 16 MB, and it can go up to, I think it varies on like browser to browser. You can allow or disallow if you want the WASM to grow itself beyond a certain point, capped by the total memory, or if you want to like disable or enable exceptions. Do you want to enable network layer? So you'll have to use fetch. And then there is one for using threading in your WASM environment. So again, like one thing to remember, if you are trying to compile for something, look out if there's a flag that you have to enable. Mostly the compiler should like flag you with errors in such scenarios as well. So once you have installed and activated the EMCC on your shell, you should run EMCC -v to look at the version, and that should ensure that you have the SDK set up right. Now, while we look at a sample C++ code, which is again very simple int main printf hello world return 0. Now we can compile this code to WASM in two different ways, or rather three. So we can either get like a standalone WASM, we can get a standalone WASM with a JS glue, or we can get the standalone WASM, the JS glue, and also the HTML file that can run on the browser. So to, let's say, output both the glue um, file of JS and also the WASM, we can use EMCC, the CPP or the C file, and the output hello.js. And now hello.js would contain the code so that you can directly embed this into your browser or run via the node environment so that your WASM code runs appropriately. Or if you want to run it directly in the browser via the HTML, you can after the output use the file name with .html suffix, which will create three files: hello.js, hello.html, and hello.wasm. Now, as I said, once the JS file is available, you can either run it through Node.js or you can directly embed that in your script as is mentioned here, and this will be loaded in your browser again. Or you can directly run the HTML created by -o hello.html directly into your browser, and that should automatically load the hello.js, and hello.js will load the WASM. So that's the chaining that happens, and that's how you can create the output from the compiler. Like GCC and Clang also generates unoptimized code by default, and I think that's the default as well. Like if you want to, if you're starting in compiling your code, you should check if everything is working without optimization. And once you've made sure of that, then we can pick and choose the aggressive optimization techniques that are available. So, I mean, there are levels from O0 to O3 available for speed, and then OS and OZ for code bundle size reduction. Now, it is also like possible in normal C++ application, but for WASM, let's say if your home page is dependent on a WASM, so you might want to reduce the code size there because the load time basically is very critical for any home page or any page to be cited very well. So yeah, I mean, pick and choose the right optimization flag that you want. And then while you first time compile the WASM library, the system libraries will be generated and cached there. Now, one of the things, again, to remember with system libraries and reported depths is that EMCC is providing you with the own implementation of all the header files and system libraries like stdio file system. There'll be like a separate implementation from these, apart from, let's say, a Mac or a bin implementation that's already available by the system. And then most of these are actually based on WASI, which is allowing us to run the same WASM code across different platforms. So if the API is WASI compliant, that should be pretty simple. And then with the system libraries, there are so many other libraries that have been reported for any of us to use, like Boost and SDL. So you don't have to do the heavy lifting of porting these well-known libraries to WASM by yourself. Now, let's look at some of the call interaction that happens across the different layers. So we are taking an example of browser here, not the backend, which could be like Node.js. So for the browser itself, there are 4 things into picture, like the browser, there's a WASM file, the script file, and the index.html. Now, if you see, there is a breakage, there is no linkage between the WASM file and the HTML file, and that's because the WASM cannot directly contact or call the DOM APIs. It cannot manipulate the DOM itself. So it needs to go via the route of script, JS, or basically the JavaScript, and then JavaScript can actually manipulate your DOM. And then WASM will directly run on your browser, and then JavaScript can interact with the browser as well as HTML. So I mean, that's one of the things to remember. So if you have to make any changes to the DOM, you have to write JavaScript code in your code. Now, I think it's a good time to actually switch to our hands-on session. So before we dive in, I'd like to probably go through the setup. So this is our IDE. This is the terminal. We're running a Docker, which is, again, as I said, is available on the GitHub repo. So this is my console of the Docker. And this is the local host that we're running on the Docker. And we are just looking at this to go through multiple examples. So let's start with the first one and the very basic one. We want to achieve two things in this example. First, we want to call a C++ API from JS. And the second thing that we want to achieve is call a JS API from C++. So let's start from the top. You see two new headers being added, mscripting.h and mscripting-bind.h. mscripting.h is needed for basically compiling into mscripting world, and then bind.h is required for something known as mscripting bind that will go over in the further of this example itself. Now, going to line 18, which is the most comfortable for all of us, it's a simple C++ function which says void and the name add label, and it takes text as an argument to itself, and then it further calls a function JS add label. Now, what we want to achieve is we want to call this add label function from our JavaScript side. So what will we have to do for it? There is something known as mscripting binding code block available or block available in mscripting for us to allow any of the C++ constructs to be available in the JavaScript world. So the first thing that goes inside of it as an argument is the module name. Now, this could be anything of your choice that you want. Now, there is an mscripting function available, which would allow you to bind a C++ function to a JS function. So the first argument is an add label. Now, this could be anything. And this is a name that this function would be exposed out in the JavaScript. And the second argument is the function pointer of that's available in the C++ code itself. Now that this is done, the second step that we would like to achieve is calling a JS API from C++. So for that, we are using the emjs block available again with mscripting. And this purely allows us to write JavaScript code in a code block within the C++. Now, even if you write something crappy in here, you might not get compiler errors. You will get runtime error because this is purely a JavaScript and will be interpreted on the runtime itself. Now, in this function, in this block, what we are trying to do is define a JS add label, which can be called from a C++ API. It takes an input of text. We convert that const char pointer to a JS string with UTF-8 to string conversion. We create a new H2 element with document.create element. Now, document you see is not available anywhere because this is something which is already available with a JavaScript context. And that's where I'm saying this is all JavaScript that you're writing. You add an inner HTML to your node, and then you add this node to the body of your document itself. And now that this is done, let's actually compile this. And we looked into the compilation in the slides. So the first is my CPP. The output is the glue.js. And then I'm using a bind flag. Again, as I said, there are certain flags that you have to enable. So for enabling binding of a C++ to JS, we are sending in this flag. Now, these two outputs are created, simple interfacing.js and WASM are created by compiling this code. Now, let's quickly look into our HTML. So I think all of the other things might be pretty familiar. There are different tags for HTML, head, meta, title. The new things are from line 8 to 16. Now, line 16 is just importing your newly created glue file, sample interfacing JS into your HTML. But the line above it is actually handling a callback on runtime initialized. Now, this module function is basically what your WASM would be contained in. And if you see, it's already there even before we started to look in importing the JavaScript. So that's already available in the JavaScript. And then on runtime function initialized is called by the EMCC in the WASM. So once that is loaded, we'll get the module loaded function, and then we can call any of the function that you've exposed in C++. And this is one function that we have exposed. So now let's move on to the HTML file here. And let's also open up our debugger. So we see this console log module loaded object, and this is all the things that are there in that module object that we see here. And with the module add label, we have added a label to our DOM, which we see here. Now we can do other things here like add label, hello people. And this should come up on, okay, it says add label. Okay, I made a mistake. Add label. Okay, that comes up on the screen as well. So yeah, this is now calling a C++ function, and C++ function is again calling a JS function. I think this is good for a start, but let's dive in a little deep with further other constructs of C++ and how do we expose them. So the next thing that we are trying to expose is actually a CPP class, which is named as CPP class. It takes as an int as an argument for the constructor, and then it saves it in the data member. Now, if we want to expose out a class, we again go back to our EM script and binding block, in which there is a class underscore method available for us exposing out objects or classes to the JavaScript. Now, prototypes and classes in C++ and prototypes in JavaScript aren't like equally compatible. So there's like a difference there, which one must know. So to use like class underscore, the first argument that goes into the template is the name of the CPP class that you're trying to expose. Now, this is the name of the class that goes out in the JS world, and this could again be anything. So it's just like binding the pointers from C++ to the JS. And then the next is the constructor, which takes int as an argument. And then for exposing our data members, we use a property function. The first is a name in the JavaScript, and then the function, then the pointer of the member. And if we had to expose out like a function, we'll use dot function there. So now let's move on to the example with more C++ construct. And as we have seen, like we have exposed out CPP class here. So we should be able to pretty easily like do CPP class and add a number. Let's say give it X number. It says new. Okay, yeah. So we'll have to like this, and then if I do X dot member, I should be able to call the data member, and it gives me the right value. Now, one of the things to remember here is that the lifetime of the object isn't managed automatically by JavaScript. So you'll have to call like x.delete to be able to like delete any of the functions or any of the object from JavaScript, so that the destructor in the C++ is also called. So that's one thing to actually take into picture. And in the slides above, we also talked about like there is no GC, automatic GC available. So that's one thing. Now for the fact, if you want to like enable templatized classes in JS, like how do we do that? So this is a template class, which take T as an argument to the template. And then there are 3 arguments to the constructor. And then there is a function get member to get an appropriate array index, like value at the index of the array members. Now for that, we again go back to our class underscore construct. We send the template class. Now, one of the things with templates is we can't expose the complete template class to JS. We'll have to like give out a specialization of that template out in the JS world. So you'll have to like repeat that code over and over again if there are like multiple specializations that you want to use in your JS. Again, like this name could be anything. So we have used like in template CPP class. And then the constructor was taking like 3 arguments of the same argument type that was given by the template. So it's int here, and then the function is exposed out with function construct and the get member name in the JS world and the function pointer from the CPP world. Now, again, because this is exposed out, I can simply do new module dot, the name is int template class, and then I can do 1, 2, 3. And I can do like get member, second index should be 3, and that's what I get. So this is how you expose out like template classes. Now let's go a little deep and look into this class logger, and we'd actually be like bubbling up or like expanding our logger class, and we'll be adding like multiple functionalities to it. So it might be good to like get an overview of it right now. So the logger class is a constructor which I'm printing out both in constructor destructor when the function gets called. And then there is a log message, and the log message calls an internal function underscore log, which tries to call and add the text that has been given to the logger onto the DOM itself. Now, this has been exposed out in a similar manner. The class can be exposed out in a similar manner as CPP class. But the thing that has changed is now we are trying to expose out a shared pointer. Like if you want to create like a shared pointer of logger, which makes sense, like you want to have like a single, let's say, logger to be used across different places. So for that, there is a construct known as smart pointer, and that understands that you're trying to actually like expose out a shared pointer. So the input to that is the shared pointer and the specific class of the specific class in the shared pointer that you're trying to expose out. And then this is the logger, which is the function that you're trying to expose out. And you give make shared as the pointer out, so that whenever logger is called, automatically make shared get called. and you can automatically construct a shared pointer of the logger called from JS side. And then we are exposing out the function log message as well, so that we can call this method on the logger itself. So let's create a logger with new module.logger. Now this should create a shared pointer. So you see like logger constructor get call, and if you see the JS object logger, there is like a pointer handle there, and then there is like smart pointer that is holding on to our shared pointer in the CPP world. So I should be able to call on this log message, say hello. And then because this is a shared pointer, I should be pretty easily be able to do like, or say clone. So clone would actually like increment the ref count of my logger, so that even if I delete, my destructor isn't called, but it would be called when I delete my last reference to this logger, which is Z. Once that is done, my logger is destructed. And that is how the shared pointer can be like managed across C++ and JS. And the last bit in this is like, how do we handle unique pointers in JS? I mean, so the good news there is unique pointers are like natively supported in WebAssembly. So all you have to do is just use the same mscripting function. And this data type is automatically understood by the side on the JS. So you can pretty simply do var logger again and new module dot unique pointer. And so, yeah, I mean, there's no surprise on the unique pointer side there. So I think, yeah, that's, I think, a good overview. Let's get back to the slides. So we covered, I think, EMJS in our code sample, but there are other ways to actually call JS in your C++ code. You can use emscript and run script, or you can use EMASM, or there's also val construct available. So there are multiple other options to call JS, which one can choose from. And then for like exposing out, there is mbind construct that we read about, and all the things that can happen. There is like value class, like value-based objects, and then classes, primitives, smart pointers, templates, like all of that can be done. You can also expose out like abstract classes that you can inherit in the JavaScript. So that's also possible. Now, actually, let's deep dive into like what it takes to porting a C++ application to WebAssembly, and Pranay would actually like help us in that. Over to you, Pranay.
Thank you, Nipun. That was so wonderful. I mean, so how do we port a typical C++ project? There are various aspects to it, and it can be construed in three main blocks. First is you port the application logic. This application logic is what your C++ code would be doing, and your UI logic that manipulates DOM or renders on the final web app could be anything. It could be React, it could be TypeScript, it could be anything else. So the application logic you have to port to WebAssembly. Then there might be some dependencies that your library or your code uses. You have to port them to WebAssembly as well. And the good part would be there might be some pre-ported libraries such as Boost and SDL that we covered previously in the slides. So that part would be already available to you and that you can leverage. Now, let's see what do we have to do in order to port a network layer. For various operating systems like Mac OS, Windows, they provide their own networking functions. And so that's why emscripten also supports libc networking functions. It gives you certain constructs, and you must use them using the given asynchronous operations in order to access and use the network layer. The applications have a number of ways to connect with the online servers. The WebSocket support is there, which is pretty good. POSIX sockets are also supported. Then XML HTTP request and Pitch API support is also provided along with the emscripten. Again, you have to provide the configuration option. You can do request, HTTP get, put, post, delete, all sorts of requests from your local or even from a cross-origin server, but you have to compile with the -s fetch options. The good thing is you can choose to persist the downloaded files locally in browser's IndexedDB. So IndexedDB is just a persistent relational storage based on the browser. That is what emscripten can also enable you to do. You can persist the files there, and they can be re-accessed locally on the subsequent page widgets. Let's see one example here. So on the third line, you would see the fetch.h header is being used because we are availing some constructs for accessing emscripten's network layer. And there is a download callback. There's an error callback specified here. So em script and fetch attribute is the construct using for network layer accessibility, and you can specify that you want which method to use, such as this is a get request. You can specify how do you want to load files. In this case, we are loading the files directly to memory, and we are basically accessing a file myfile.dat onto our own server with a get request. So as soon as the em script and underscore fetch is fired, depending upon how the request went, error and success callbacks would be called. Let's cover the storage layer. So in em script, your code runs in a browser environment which is sandbox. Your tab doesn't have the direct access to local file system. So what em script has done is it has provided a virtual file system that simulates the local file system. So your native code that uses synchronous file APIs such as fopen, fclose, ifstream, ofstream, they all would work well, and you can do away with very little or almost no change. The good thing is you would need to just mount either of the given file system, and your fopen, fclose, all these synchronous files APIs would work well. So you may preload your data with, you may preload your application with some specified data, or you can link to some URLs if you want to have the lazy loading enabled. The other option that you can choose is you can also cache your files for the current session for a transient operation, or you can also persist them across sessions depending upon your use case. Let's see in this diagram is so this is how a web typically looks like that uses storage layer of em script. It accesses the libc and libc access provided files APIs which are synchronous. There are also asynchronous file system APIs available that JavaScript can also use. Even your C++ code can also use if you want to, but most likely you would be porting some code for your existing project, so you would be more comfortable with using the synchronous file system APIs. Then there are multiple kind of file system and objects available here. One is memory.fs, which is the volatile in-memory file system that is available to you by default. Second is IDBFS. It's a browser-based layer, which is implemented on top of IndexedDB. It's a persistent layer. So if you want to cache users' preferences or anything else, that is your best bet. Then comes a Node.fs. If you're running in a Node.js environment, this is what you use. And there's a proxy FS also available. If you are referring to some other WebAssembly module, you can mount their file system in your proxy file system as well. Let's only memory FS, because it's volatile, it's in memory, it's included by default. All others have to be enabled explicitly using their linker commands. That is link node.fs.js, link idbfs.js, or proxyfs.js. The FS object, that is the asynchronous file system object, you can use it from JavaScript as well. And if you don't want C++ code to use the file system, you can perfectly avail it from the JavaScript only. But the only thing is that your code, your compiler wouldn't know that it's referring to the file system. So in this case, you would have to specify a linker configuration that you want to link with force file system. That makes the compiler include file system, even though it doesn't see it being used. Let's see this example. So in this case, the asynchronous file system object, this code runs in the JavaScript. For example, you can create a directory /persistent, and it's mounted on top of IndexedDBFS. And there are various functions available, such as syncfs, which basically allows you to sync from the persisted state into the memory, and you can your code, your file system would be then ready to use, and from the last session, whichever was synced. Then comes the exceptions. So by default, exception catching is disabled in em script, and executing a throw would abort your program directly. And you would see similar messages below that it's disabled, it cannot be caught, you need to specify something and something. So if you want to opt in for the exceptions, you have two following options. You can opt for the JavaScript-based exceptions, or you can go for the native WASM-based exceptions. What JavaScript-based exception support is that it's supported on all the major browsers or JavaScript engines. The good thing is it's universal. So in order to enable it, you need to pass -f exceptions flag at the compile and linking time. And the bad thing about is that since how WebAssembly implemented these JS-based exceptions, this option can punish you with high performance size penalty. Your application bundle size would be increased and the performance would be reduced. So you can reduce some of the overhead by specifying a list of whitelisted functions with the exception catching allowed option. WebAssembly exception handling is a proposal because it's not supported universally yet. It's supported on few major browsers. In order to enable it, you need to pass -f WASM exceptions at both compile and linking time. The good thing is this feature has built-in instructions for throwing and catching exceptions to WebAssembly, so it's pretty fast. Practically speaking, one should build two versions of WASM, one with exceptions enabled, the other one without it. So in production environment on runtime, if you see somewhere exceptions have occurred, you by default go with the disabled build, and if in case exception is occurring, you can switch to a less performant or the enabled build. Now, typically in native environments, we have application main event loop handler. For browser, there is already event loops that uses cooperative multitasking. Each event gets a turn to run, and then it must return control back to the browser so that events can be processed. You might have seen this kind of cases that your page is unresponsive. So that usually happens because your JavaScript code, which is being executed, doesn't return control back to the browser. However, this can have impact on the application that uses infinite main loop because it's not scalable for web. So you get an option to specify a custom event loop using the EM script and set main loop argument. This event loop can be later cancelled easily as well. So that is the link so that you can read into it more. Now I hand it over back to Nipun so that he can give us some hands-on session on how to do a practical coding over the logger class.
Thanks, Pranay, for such a wonderful explanation. So I think our next steps here is we'll try to expand on some of the learnings that Pranay has taught us on, and then look at those through the eyes of a logger class that we'll try to expand. So again, like the logger class we used in the last time, here we were trying to like. So now what we'll try to do is add an IndexedDB extension to our logger. And IndexedDB is basically, as explained, it's a persistent file storage in the virtual system of the browser that exists for us to be used across sessions. So as any log call is made to the C++ side, we'd also want to add that to the IndexedDB so that once we refresh the browser, we get that same data again and could be read from. So to enable that, I think the first step that we want to add is like change our logger class a little bit. And we are in the constructor itself, setting up the file system. We are using the synchronous file system here. So the first thing that we do is we call the make directory function, and we are using like a data directory here. This could be anything. In the slides, it was persistent. For here, like we're using data. Now we mount this directory into the virtual file system as a IDBFS, which is IndexedDB file system. And the second argument is like multiple options that you can do, like mount this file as well, mount this blob. I mean, there are so many other options. We are not using any. And then last, we synchronize our virtual file system to have this IndexedDB to be read and be used by the code itself. So now when anybody actually logs a function and calls the log function from the JS side, we call the internal underscore log. And that simply opens up a file in this directory that we created, named as logs. And it appends all the new string that are coming in. And then after that, there is a column. And then post that, we call a syncfs function. Now, this could be your choice. Like, when do you want to call it? We are calling it after every iteration right now. But this is essentially needed before you actually like reload your browser. So because in case like you don't call syncfs here, essentially all your local changes aren't synchronized with the persistent storage. They'll still be in your local IndexedDB itself. So it's pretty important. But this could be chosen like where do you want to call it. And then finally, we are calling the same function utilized from our previous session in terms of like adding the log also on your console and also on your DOM. So the beauty here is our already known setup of and the APIs for file system are automatically working. We don't have to really learn a new thing here. So let's actually go ahead and compile this. To be able to do so, we again are using the CPP, and as the output, we are outputting the glue file. We're using the same bind to bind the logger class to the JS. The new thing here is also linking the IDBFS JS so that the compiler knows that we want to use the IndexedDB here. So once this is done, I'll log into our sample. Again, I think we are pretty comfortable here. So we'll create a logger class again. Okay, it says Okay. I think we already created a class in object here, so we can just use that because it's trying to like reload the same file. So now I can basically call log message hello, and this comes on the DOM. It also logs on the console, but now it is also synced to the file. I can probably add something else as well. And then if I refresh this and I try to read from my file, there's a simple way to read that, which is fs read file. And the fs read file gives me like an array of characters. So I'm just combining that using string.from char code. And this is all we get, like hello CppCon, hello CppCon. The earlier ones was from my dry runs that I was trying to do for the session. But again, this is pretty simple. So I can add something else and this will be synced. And if I refresh my browser, I can still go ahead and look into the new data that's being added. So the good thing, whatever we are trying to write is persistent. It's not getting lost, and we can utilize simple file system APIs on C++ to get the maximum out of them. The next thing that we are trying to add to our logger is also a server. So what we are trying to do is also post the message that's coming from JS onto the C++ to a server. I'll take a second to like go over the server. It's pretty simple using Botter, and it's exposing a post API log, which will take any data that's being present in your body and then append it to its own list of logs. With the logs function, it will give you out all the logs, and with the delete, it will delete any of the pre-existing logs. So let's try to access this here. So if I do logs here, this should give me the previous log. So I can possibly call delete here, delete any of the previous ones. So this deletes any of my previous ones. So now what I want to do is I want to call the log post query to add new messages that I'll send from the browser right away so that it's also logged onto the server. Now to be able to do so, again, we modify our logger class. With the log message function, we call the post to server C++ function to be able to fetch, to be able to make a network call. For that, we also add a header file mscripten fetch.h because we'll be using construct from that header file. So the first thing we do is we create an attribute, we initialize those attributes, and we change the request method to post for those attributes. Again, we change the attributes to fetch load to memory rather than keeping that persistent in the like IDBFS. Like one thing is like we can download something and then put it in the IDBFS itself. Right now we are using the memory itself, like in memory usage is being done. And then I'm adding whatever data is being sent as a request data, and I'm also like setting up the data size for it. And then I'm making the mscripten fetch call to log, which is on localhost. So there's no appended HTTPS google.com something. And then %attr is like giving the attributes that we have declared here. So now that this is there, I log into my logger method, and we have created again a logger obj here. So this is IndexedDB. So let me just go to the server one, and I can call logger obj log message hello. And once this is done, I should be able to like make a look into my logs, which is now present here. I can do by, and then I should be able to like see that on my server itself. The other like debugger is very useful in these scenarios. So I can should be able to like look at the log post queries that I'm making in the network tab itself. So these are the post queries that I'm making to the /log, and this is the post query with the payload hello. So that's how we make a network call and make our logger a little bit more useful. On to the last example that we want to try out is, because we're adding so much functionality to our logger, we want to make sure that we are actually doing that on a separate thread. So we'd also like to add a different thread to our logger. Now, one caveat on that is that threads use shared array buffer, and that needs to be enabled on our Chrome. So we are using terminal flags to enable shared array buffer, which can be again looked up in our README, and we have specified the flag that you have to send in to enable the shared array buffer support in the browser. So again, our logger has changed a little bit now. There is a new construct that you see, or a macro, which is mscripten pthread. One thing to remember, you can either compile your code for threading or without threading. You can't not compile for like you compile for a single threaded, and then you cannot expect like threads to be spawned out in a runtime manner. So you'll have to like make a preemptive decision on that. So there's an mscripting pthread now available with the option that we give, like use pthread into the EMCC. In that, the T1 thread is being assigned with a message with a function like wait for message. It's basically like running on an interval and checking the queue. If there is a new message in the queue, I'll pop that out and I'll call our internal log method for that message. And the log message that exposed out to the JS is basically like taking a mutex and then pushing things in the queue so that there is no conflict while the other thread or the JS thread is trying to like read this. So that's how like we are basically enabling the C++ threading support in WASM. Now to compile this, we are adding two new flags to it. Use pthread, which is essentially needed for enabling multi-threaded, and the second one is pthread pool size, which sets up like how many workers or like threads do you really want, and then you can also like play around with it, or there are other flags to like say strict no, or just you don't want to like give it and let it grow as the runtime requires it. So I mean, there are like multiple flags to look into for how many threads do you really want. So let's go into our sample for threading. And once we run this, I mean, the first thing that we'd like to check is, do we get two threads? And in here now, if you see like there's a main thread and then there is also like a worker thread. So essentially that's enabled now, and we have like two threads for us working. Now going into the console, I again in the HTML created logger.obj, so I can simply go ahead and log my and now this is being thrown out from the thread itself, not the main thread. So now you can leverage your thread to do multiple other computation options. And that's how we can actually like enable porting our C++ application with the use of threads. And with that, I think it's a good time to switch to how do we really debug all this WebAssembly code that we're writing in C++ into the browser itself. And Pranay would help us explain that.
Thank you, Nipun. So what debugging is, it's like being the detective in a crime movie where you are also the murderer, or if you're handling a legacy code, probably someone else is the murderer. How do we debug the WebAssembly? We do it via dwarf, which is a debugging file format used by many compilers. To do the source level debugging, we can debug C++ code directly in the Chrome by using this information. The emcc-g flag can be used to preserve the debug information is compiled output. And this -g flag can be specified with an integer level such as -g0, g1, g2, and g3. -g0 where it specifies maximum optimization, and -g3 means preserve everything on. So this is the default setting where you're compiling for debugging. How do we achieve this magic? So there are 3 steps to it. You need to install a Chrome extension, then you need to enable the DevTool experiments, and then you need to recompile your code if you haven't done already. Yeah, this is something of a caveat probably. So you thought you had all the tools, but you need to do this one-time off setup. So this is the Chrome extension that is available for the debugging. You can install it via Chrome Web Store. Then you need to open your DevTool experiments, and there's a check that says WebAssembly debugging enabled WAF support. So you can check that. You can reload your DevTools. And you need to provide -g flag while comparing your library and your source code. So once you have done that, you wouldn't see a change right away, but in your DevTools, you would see add folder to workspace, where you might need to add source folder to workspace. That is one time. You can select the source code folder there directly. And once you do that, you'll see the files listed on the left side, such as hello.cpp is shown here. You can add a breakpoint on any file, say line number 5, we've added the breakpoint, and then you load the web page. That is it. So the breakpoint has been hit, and you can see directly source level debugging happening here. On the left side, you see the source tree. And on the right side, you see all these other information such as step into out, step next, list of break and watch points, your scope, your variable values, your call stack that is happening across the WASM calls. So if you want to debug optimized builds, that's okay, but you need to be aware of the inlining that may be happening by the compiler. So in order to avoid that, you need to compile with -f and no inline option. There are some traps and cautions that we have learned over the years, and we would like to share them with you as well. So first is file system access. Default file system is virtual and transient. As soon as you are away from the tab, the data is gone. So if you want to persist them, make it explicitly noted in the file system that you are going for the persistent index DB. Then there is the memory limit option. So by default, Chrome has 4 GB limit, and in Firefox and Safari, it's specified to 2 GB. Then zero cost exception handling is not there for JavaScript based handling. The limited support for WASM based exception handling is there, but that's already available in some of the browsers. Then your main UI thread shouldn't be blocked. If you are running for large loops or computations, you might get a browser notification that it wants to kill the page. So you can specify a custom event loop using the em script and set main love argument that can be cancelled later. And as a good practice, if your code is computation intensive, you should run in a web worker that keeps the main browser thread free so that you can continue to render and you can handle user interactions that are happening over the page. The thing is that web worker and the main thread would need to pass the messages and they need to handle their callbacks and events. So it all depends upon what is your payload size when you're transferring the message from your web worker to your main thread. And if the data side is large, you might have to go for a trade-off among these two approaches. So that's all we had for this presentation. We hope you liked our content, and we are open to for question and answers.